Okay, let's take a look at another conservation of momentum problem. Again, we have to look at momentum in two dimensions, in the x and y dimension. This one's a little bit different than the other problem I had done. We have a 10 kilogram projectile. It's moving at some velocity, only in the x direction, not in the y, and it explodes into 3 pieces. Lovely. We want to figure out the speed and direction of the third fragment. And so we have some before information. We have a little bit of after. On the third fragment, we don't know its mass, angle, or velocity. That's all the stuff we want to figure out. Well, the mass is pretty easy. I think it's safe to say conservation of mass, if we begin with 10 kilograms. Here's 3, here's 3, so this mass must be 4 kilograms. And so I'm 1/3 done. Again, this is a conservation of momentum problem. And so what I know is that my before momentum is equal to my after momentum. Now, unfortunately, it's a little bit more complicated than that, because what we have to look at is my momentum in the x direction before. So my initial x momentum is equal to my final x momentum. And the same thing for my y. My initial y momentum is equal to my final y momentum. But this particular problem, we're going to have to look at momentum in both the x and the y. So let's take a look. What's my initial x momentum? It's just the momentum of the object, which is 10 kilograms times 2 meters per second. So we have 20 kilogram meters per second, some awesome momentum units. My momentum in the y direction initially is 0, because I have 0 velocity in the y direction. And then I'm going to break up and I'm going to take a look at all my after momentums as we go through the problem. So let me just erase this x momentum. And my before momentum is 20. I'm going to leave off the units. My after the momentum is momentum of object 1 in the x direction after the collision, plus the momentum of object 2 in the x direction after the collision, plus my momentum of object 3 in the x direction after the collision. Those two terms are equal to each other. So what this means is 20 is equal to, well, this mass 2, this x velocity, this velocity is all in the x. And since it's in the negative direction, it gets a negative 10. So I've got that velocity. I know all the masses. Velocity vector for object 1 can be broken down: so much is in the x, so much is in the y. And so my x component is going to be velocity 2 after the collision times the cosine of 40. My y component, which I'm going to need anyway sooner or later, is the velocity of object 2 after the collision times the sine of 40. And I'm going to do the similar analysis for object 3. There's my overall velocity, which is v3. Actually, it's v3 prime. I can break that down into some x velocity, which is going to be v3 prime cosine theta, and some y velocity, which is v3 prime sine of theta, but this is going to be negative since it's going downward. And so I'm going to set up and I'm going to rewrite my conservation of momentum in the x direction as Now I have numbers for my masses. This is 3 kilograms, 3 kilograms, 4 kilograms. I have this velocity. This is 12 meters per second. The only thing I don't know is I don't know V3 prime and I don't know theta. So I can simplify this down, and actually I'm just going to go ahead and simplify it down with the numbers. So just give me a second to do that. So that's what I get by plugging in the masses and the velocities that I know, and then solving and rearranging this expression gives me, or even simplifying it further. And so just kind of a slight rearranging, V3 prime cosine theta is equal to negative 5.6. Now, I have two unknowns, which means I need a second equation, which is going to be my y component, which is 0. My initial momentum in the y direction was 0. And that makes this m1 v1y prime plus m2 v2y prime plus m3 v3y prime. This is 0 because the second object has no y velocity components. So I'm going to go through and using this information for my y components, I'm going to plug it into this expression. So I've gotten the y velocities using these y velocities right here. I'm going to plug everything into my conservation of momentum in my y direction. In other words, I have 0 is equal to, and then I'm going to take m3 v3 prime times the sine of theta, but this is a negative sign because we have a negative y velocity component. Be very, very careful about that because I made that same mistake. Now, plugging in for my masses. So I have two expressions. I have V3 prime is sine theta is equal to 5.8, and then from my x direction I have V3 prime cosine theta is equal to negative 5.6, and what I need to do is solve these equations simultaneously. I think I'm going to say V3 prime is equal to negative 5.6 divided by cosine theta. And then I'm going to plug that in, and I'm going to say negative 5.6 over cosine theta times sine theta is equal to 5.8. So I rearranged this equation for V3 prime, and then I stuck it into that equation. And what this gives me is sine theta over cosine theta is equal to 5.8 over negative 5.6. Sine over cosine is tangent. So the tangent of the angle is 5.8 over negative 5.6. So by taking the inverse tangent of both sides, I can get the angle. And I get negative 46 degrees. And it's negative because it's going down. That makes sense. So I got an angle of negative 46 degrees, which is fine, because what that means is that's 46 degrees downward. And that's okay. There's no issues with that. What you do have to be careful about is when you're calculating the velocities. We've already gotten the direction accounted for. So I'm just going to look at absolute values. I know that sounds a little confusing, and I'm simply going to take this angle and I'm going to plug it into that expression. In other words, and what that gives me is just over 8 meters per second. I know the signs can get a little confusing, and what you have to recognize is whether we're using the sign for direction or not. And this negative sign is for direction, which tells me it's down. That's fine. That's supposed to be expected. But I'm not going to get a negative value for the magnitude. And that's why I kept everything positive. So this might have been a little bit more complex, a little bit more in-depth, a little bit more algebra and trig, but simply doable if you have the patience to plug through it. If you can do this problem, you can do pretty much any type of momentum problem that in regular physics is going to encounter. That's all I got for you. Good luck.